Hello and welcome. We have mentioned before that motion drives are connected to the system controller as an output. Such a motion drive is the contactor. A contactor is a relay device that consists of a coil, a plunger, three bars attached on the plunger, three normally open contacts, and a spring. When the coil receives a control signal, it generates a strong electromagnetic field that pulls the plunger in. The three bars will close the normally open contacts, connecting the motor to the voltage lines. If the control signal is switched off or disconnected, the electromagnetic field collapses, the spring force takes over and pushes the plunger back, and the normally open contact goes back to open. The device on the right is a thermal overload protection device. When the motor is subjected to overloads, it draws a high current which heats up the wires and burns the motor. The three heater sensing elements, they sense this heat and mechanically open the normally closed contact when the current reaches a predefined set value that may cause damage, commonly 15 to 25% higher than the normal current. A solenoid-operated DCV consists of a coil, a plunger, a spring, a 3 to 4 inlet and outlet ports, and three rounded bars called lands attached on the plunger. When the solenoid receives a control signal, it generates a strong electromagnetic field that pulls the plunger in, causing the lands to shift, connecting the supply line to the inlet line and the outlet line to the return line. If the control signal is switched off or disconnected, the electromagnetic field collapses, the spring force takes over and shifting the plunger back, and the ports will be connected to a hold or return position, in our case to a hold position. It's also worth to mention the working principle of the other relay devices. A control relay device consists of a coil, a plunger, sets of bars attached on the plunger, a set of normally open and normally closed contacts, and a spring. When the coil is energized, it generates an electromagnetic field that immediately pulls the plunger in. The normally closed contact will open and the normally open contact will close, sending a control signal to a motion drive like a contactor. If a coil is de-energized, the electromagnetic field collapses immediately, the spring force takes over and pushes the plunger back, and the contacts goes back to their normal state. The timers are pretty much the same. In addition, they have a clock mechanism behind the scenes not shown. For the on-delay timer, when the coil is energized, the plunger is pulled in after a delay time, and when the coil is de-energized, the plunger is pushed back immediately. Below is the time transition diagram. The input is the coil and the output is the normally open contact. When the coil is energized, after a delay of 1 second, the normally open contact closes, and when the coil is de-energized, the contact is sent back to its normal state immediately. And since the clock is set to 1 second, if the coil is energized for half a second, then the contact just stays at normal state. For the off-delay timer, when the coil is energized, the plunger is pulled in immediately. And when the coil is de-energized, the plunger is pushed back after a delayed time. Schematic symbols are shown below. This is a normally closed and that's a normally open contact. The pulse timer is halfway between the off delay and the on delay timers. When the coil is energized, the plunger is pulled in immediately and during this state the contacts goes back to their normal state after a preset time, which in our case is 1 second. Anytime the coil is de-energized, the plunger goes back immediately. A system controller connects input devices like sensors and switches to an output devices like indicator lights and motion drives such as DCVs, contactors, and VSDs. Based on the condition of the inputs and how they are connected, a logic decision is made to take an action. For example, switching on-off output devices or change speed. Such a controller is a hardwired logic, where the logic decision is determined by the way the devices are electrically interconnected. Hardwired logic can be implemented using relays and relay ladder schematics. It is very important to visualize and understand the logics before diving into PLC programming, since it's a logic-based programming. The logics can be expressed in ladder logic, logic gates, Boolean equations, and truth table. There are a total of 8 logics, starting with the AND logic. AND logic can be expressed electrically by hardwiring devices such as push-button switches and indicator lights. Since it's an electrical circuit, we need a power supply and wires in addition. To make an AND logic decision, the two normally open switches are connected in series to turn the light on. So only when pressing switch A and switch B, the light turns on. The schematic drawing shown is called ladder logic, where the power supply is the two vertical lines, the wires are drawn in a straight line, all input devices are on the left side, and only one output device per complete path or line. AND logic can be expressed electronically by a logic gate. A logic gate is a digital integrated circuit with the multiple inputs and only one output can be activated. The schematic drawing for this logic gate is the D shape. The truth table is a two-state binary concept used to express the logic function by the possible combinations of input conditions. The 0 means the switch is not pressed, and 1 means the switch is pressed or actuated. There are a total of 4 possible combinations with using two switches. First combination is when both switch A and B are not pressed and the light is off. Second is when switch A is not pressed and switch B is pressed. The light is still off. Third, when switch A is pressed and switch B is not pressed, the light is still off. So only when switch A and switch B are pressed, the light turns on. The Boolean equations are used to express the mathematical function of a logic. For AND logic, A multiplied B will give us these results, and the dot is called the AND operator. Moving on to OR logic, the ladder expression is two normally open switches are connected in parallel to turn the light on. There are 4 possible combinations when using two switches. When switch A or switch B is pressed, or both are pressed, the light is on. The mathematical function is A plus B will give us these results. The logic gate is the symbol shown. For NOT logic, the ladder expression is only one normally closed switch connected in series with the output. There is 2 possible combinations using one switch. When switch A is not pressed, the light is on, and when switch A is pressed, the light is off. The mathematical expression is A inverted, indicated by a bar on the top of A. A triangle shape is the logic gate symbol. The bubble on the output is to invert the signal. The logic expression for NAND logic is two normally closed switches are connected in parallel to turn on the light. NAND is the opposite of AND. Where AND uses two normally open switches, NAND uses two normally closed switches. In AND, the switches are connected in series. In NAND, the switches are connected in parallel. Looking at the truth table, NAND results are inverted AND results. The mathematical expression is the inverted AND expression, or ask yourself how you can turn on the light. Is when switch A is not pressed or switch B is not pressed. The inverted AND gate is the logic gate symbol. The bubble on the output is to invert the signal. Moving on to memory 1, the simplest logic expression is one normally open switch as a start condition connected in series with a normally closed switch as a stop condition to energize the relay coil CR1. Using one normally open relay contact CR1A to latch and another CR1B to send a control signal to an output device. The latch contact provides an alternative route to complete the path, keeping the coil energized when the start switch is released. So releasing the start switch has no effect or no change on the output status. One way to turn off the output is by breaking the latch, which is by pressing the stop switch. Comparing memory 1 with memory 2 is when both the start and the stop switch are mistakenly pressed at the same time. In memory 1, the output is switched off. In memory 2, the output stays on. Now, for safety reasons, we will be using memory 1 for most of the time. Practicing what we have learned, we have three electrical ladder logic circuits. We need to identify the logic or logics being performed and express them in logic gates and Boolean equations. I will do the first two and you do the third one. First one, here we have switches A, B, and C. Switches A and B are normally open and connected in series performing an AND logic operation. The result of the AND logic and the normally open switch C performs an OR logic operation. The Boolean equation is when switch A and B are actuated or switch C is actuated, the output turns on. The second, we have switches A and B. The normally open switch A and the normally closed switch B are connected in series performing the first AND logic operation. The normally closed switch A and the normally open switch B are connected in series performing the second AND logic operation. The result of the first AND logic and the second AND logic performs an OR logic operation. The Boolean equation is when switch A and not B is pressed, or switch B and not A is pressed, the light turns on. Here we have logics that are expressed in using logic gates. We need to identify the logic or logics and express them in Boolean equations and truth table. I will do the first and the third, you do the second and the last one. The first, we have signal A going into both of the NAND gate inputs. Input 1 have signal A and input 2 have signal A. Inside the gate, these two signals are connected in series performing AND logic, A dot A. And we know A multiplied by itself is equal to A. Just before the output, signal A is inverted by the bubble. So the output is equal to signal A inverted. The whole logic is equivalent to a NOT logic. The truth table is when A is 0, zero dot 0 is equal to 0, and 0 inverted is equal to 1. When A is 1, one dot 1 is equal to 1, and 1 inverted is equal to 0. The third, we have signal A and signal B. Each is going into a NAND gate inputs. The result of the first NAND gate is A dot A inverted, which is equal to A inverted. The result of the second gate is B dot B inverted, which is equal to B inverted. Both results are going into a NAND gate. The result is A inverted dot B inverted, and the whole is inverted. A inverted dot B inverted is equal to NOR logic. Inverting NOR logic gives us OR logic, the opposite of NOR. So the whole logic is equivalent to OR logic. The truth table is when A is 1 or B is 1 or both are 1, the output is 1. In these examples, we have Boolean expressions. We need to draw the equivalent ladder logic and logic gates circuit. I will do the first and the last. You do the second and the third. The first, we have switches A and B are normally open and connected in parallel, performing OR logic. Switches C and D are normally open and connected in series, performing AND logic. The result of the OR logic operation is connected in series with the AND logic operation. The last, we have a normally closed switch A, a normally open switch B, a normally closed switch C, and all three are connected in series. A normally open switch D, a normally closed switch E, a normally open switch F are all three connected in series. The result of the first AND operation is connected in parallel with the second AND operation.